I think we have reached to the point of talking about the cross sections, right? We reached to the point talking about the cross sections.
Yes, mister, this was the last slide you explained.
Okay. And then we said we are going to take the loading. There are three what you call methods, or three let's say possible loading criteria. Okay, one which is considered to be actually loaded, okay. One which is considered as actually loaded, and we are referring to that the load is acting at the center of the column. Okay, that the load is acting at the center of the column. Means they don't have any moment. Okay. They do not have any moment. Okay. So once again, the first scenario, that if we are having a column, the center of loading is acting exactly at the center. And this will happen. This will be happening. You are having a loading and a loading. We say there will be a moment here and there will be a moment here. If your M1 is equal to M2, M1 and M2 will be cancelled. So this column is not going to rotate. So this column is going to have the loading exactly at the center. If you remember, I think we have talked about the frames previously, right? Okay. So one of the criteria is whatever we call it as actually loaded, and the code says for you, it allows you to have 0.5%. So any loading within this particular region, any loading within 0.5% is going to be considered as an actually loaded. Okay. Now the equation for actually loaded, the equation for actually loaded we are using normally is n equal to 0.4 FCU, so area of concrete, plus 0.8 into Fy, area of steel. And from where this is coming, I think we have taken the derivation in design of structures 1. Now, since we're having a loading here, there will be two forces. There will be a force of concrete, and there will be a force of steel. Okay, let's say steel in compression. Okay, so we have P, or whatever we call it N. Okay, the loading, and then due to the loading, there will be stresses. Okay, there will be stresses developed by the concrete and steel. FSC is representing steel in compression. CC is representing concrete in compression. Okay, concrete in compression. Okay, and if you can calculate your value of stress using the equation, stress is equal to force divided by an area. Okay, force divided by an area, and then this can be formulated into force equals to stress multiplied by area. Then we can say N is equal to FSC plus FCC. If we are doing equilibrium, N or P, the loading, will cause me to have forces in the concrete and the steel of FSC and FCC. FSC is representing the stress in steel multiplied by area of steel according to the equation that we had here, plus stress of concrete. Okay, stress of concrete multiplied by area of concrete. Okay. Now, I think the voices. Others, you cannot hear me? Others, are you able to hear me, or it's not clear? Okay, so clear. Who will try to go out and then you come in once again? Okay, because I'm actually raising my voice. Okay. Now, what is the stress? What is the stress in steel and what is the stress in concrete? What is the stress in steel and what is the stress in concrete? We agreed. We said N is equal to, we said stress of concrete multiplied by area of concrete plus stress of steel multiplied by area of steel. What is the stress of concrete? Maximum stress of concrete. Maximum stress of concrete is 0.67 FCU divided by gamma n multiplied by area of concrete plus stress of steel is how much? Stress of steel is equal to Fy divided by gamma MC and gamma ms multiplied by area of steel in compression, let's say. Where 0.67 multiplied by FCU, since FCU is variable, it change 30, 35, 40, changing. Gamma MC for concrete is 1.5 multiplied by area of concrete plus Fy divided by S factor of safety for steel, which is 1.05. If we are using 460 multiplied by ASC. Now, if we go and divide, if we go and use a calculator, to divide 0.67 divided by 1.5 is 0.446. So we have 0.446 FCU will return back as it is. Area of concrete will return plus 1 divided by 1.05 is 0.95. Fy will return back and then AS. Now this is the equation for N if the loading is perfectly at the center. Now the code says, since we are having an allowance of 10%, we say if the loading is coming within 5% from each and every side, still it's considered to be actually loading. Okay, because in reality you cannot get 100% perfection in terms of getting the center of loading. So the code says for you, since we are giving you allowance of 5% from all sides, then this can be reduced by 10%, which is giving you approximately 0.4 FCU area of concrete plus 0.8 Fy area of steel. Okay, so this is correct if the loading is only accepted at the center of loading, okay, or the centroid of the column. The second one, if you are allowing an allowance according to the code by 5%. Okay. Now from where we have got these things, if you return back to your codes, these things you should have studied in the basic of derivation in design of structures 1. And now we'll go for the strengths. Okay, first thing is the factor of safeties. You can see 1.05 and 1.5. For steel, it's 1.05. For concrete, it's 1.5. So that's why I have used 1.5 for concrete, and I have used 1.05 for steel. And we call it as gamma. Now related to the stress strain curve, you can see that the maximum maximum stress. Maximum stress in a concrete is 0.67 FCU divided by gamma m. 0.67 FCU divided by gamma m. I'm assuming that you should have already taken this. And the maximum stress in steel is Fy divided by gamma. The Fy divided by gamma m. So there is nothing new in the derivation that I have done. Only instead of deriving it for a beam, which you used to do in singly and doubly reinforced, I have derived it for a column. Now you can see that this is the equation. Okay, this is the equation, which is n equals to 0.4 FCU multiplied by area of concrete plus 0.8 Fy area of steel, and you are allowing only a nominal eccentricity, which is small eccentricity of 5%, which is 5%. So that's the first case. Once again, the first case is when we are having, let's say case number 1 is whenever we are having n 0 and then 0, where the first number is referring to n, the second is referring to mx, the third is referring to m1. Okay, so case number 1, where we are having only n value, okay, where we are having n value, so we have only axial load, we don't have moment of x and we don't have a moment of y. Okay, so we call it as axially loaded. Okay, we call it as axially loaded. The second scenario is whatever we call it as axially loaded and uniaxial bending. What is the meaning of uni? What is the meaning of uni? What is the meaning of uni? No. Uni means one. Okay, uni means one. Uni means one. Uni means one. Bi means two. Uni is one. Bi is two. Okay, once again, uni is one. Bi is two. Okay, so we have axially loaded. It means that we have, when we say axially loaded, it means that we have a load, and we have one bending, which is referring to moment. So we have one moment as well. Okay, so once again, we have a load and a moment. And we have seen a good example in the foundation. Do you remember in the foundation when we had eccentricity? When we had the eccentricity? Do you remember when we had the eccentricity? Okay, you will see that there will be a developed moment. So for example, if we are having this scenario, okay, if we are having this particular scenario, you will see that the moment here, which is M1 for example, is larger than M2. Because of the long span of the beam, M1 is going to be more than M2. Do you agree? Do you agree that M1 is more than M2? Okay, so now what will happen? You will see that the column is going to have a certain moment, if you remember. This column is going to rotate to one side, to the greater side. Do you remember this one? And we said this value is going to be now the difference between M1 minus M2. Do you remember? First classes. Oh, okay. Now you can see. Now what I'm trying to present here, I have a long span. Let's say that this is B1. And then here I have B2. Now B1 is having longer span, the length is more. B2 is having smaller length. By common sense, the moment in beam number 1 is going to be greater than the moment of beam 2. Okay. Now, if M1 is greater than M2, then this column is not going to be in the balance. This column is going to rotate to one side. It's going to be rotating to the side of the bigger moment. Okay, so it's going to rotate at the side of B1. Okay, it's going to rotate to the side of M1. Now, how many loading do we have? We have one loading. So this is going to be case 2 now, where we are having N. We have one moment either in X or we can have it as well in Y. Okay. A scenario. Okay, let's say that this M is M1 and this is M2. This M1 is 100, for example. Okay, and this one is M2. So, for example, 50. So you will see that this column is going to lean to the side of 100. The 100 is greater than 50, so it's going to push your column. Okay, so you can have moment in the direction of horizontal, or you can have moment in direction of vertical, in terms of X or in terms of Y. Okay, in terms of X or in terms of Y. Okay. Now, if you can see here what's happening, you will be having only one moment, either in vertical or in horizontal. So either we have N and X 0, or we have N 0 and then M1. There will be only one moment, either MX or MY, and one loading. That's why we call it actually loaded. There is a value of N or P, whatever is the name. Actually, you have only one moment, either to X or Y. Are we clear? And you can see the example here. Okay, and you can see the example here where the loading is not coming at the center. The loading is not coming at the center. So if we return it back to the center, then we need to have a moment. So now we have loading and a moment. I didn't understand the question, Asma. What do you mean by how the load act in X or the column? How many directions are there? How many directions? Yeah, the load will be transferring. The load will be transferring in the vertical, but the moment will not be happening in the Z direction or Y direction. Moment will not happen in the same direction of the loading. Okay. Your column cannot bend in the same direction of the loading. And we'll see. I'll try to open for you a software and then we'll see some examples. Okay. So once again, second case is going to be actually loaded and uniaxial bending. So we learned for case number 1, we are going to use this equation to solve. So this equation we have used in design 1. If you have done the design of the column, you will be using this particular equation for a case of actually loaded column without moments. In case of having moments, I cannot use that equation. So we use normally the writing, but anyhow we use charts. Okay, we use charts. I think this is the first time seeing these charts. These charts can be seen in your, let us see. I have uploaded for you the codes, right? So if we go to BS, no, this is not yet there. BS 8110 part number 3. So if we go to the codes, I'll upload this for you. If we go to the codes, VS codes. Yes, and we'll try to go for VS 8110 part 3. VS 8110 part 3. It says for you design charts for singly reinforced beams, doubly reinforced beams, and rectangular column. Okay. So there is a way of designing the beam using the equation, and there is a way of designing them using the charts. I don't know whether you have used it in design one or not as well. Okay, anyhow, you can see we have chart for singly reinforced beam. We have a chart for singly reinforced. One is for 250, another one is for 460. And then we have doubly reinforced beam. Doubly reinforced beam for certain criteria where you can see FCU is changing and D dash over D is changing. So 25, 30, 35, 40. And you can see that whenever the grade is changing, the chart is changing. Okay, that's now for the beams. We are not designing beams, we are designing columns. So you can see from here, we are starting the column. Okay, from here, we are starting the column. Now we can see the grade of concrete is given. We have the grade of steel, and then we have D over H. Okay. By finding these things, you will make sure whether this is the correct chart or not. After getting the correct chart, you will choose how much is your N over BH, how much is your N over BH square, and you will get the value. And we'll solve one example. We'll solve one example according to that, and we'll see how to use these charts. Okay. So that is related. That's related to uniaxial. So we said axially loaded. We are going to use an equation. Uniaxial, we need to use the chart. The third scenario, which is a biaxial. The third scenario is a biaxial. Now, what you can see here. Okay, what you can see. Now, in this scenario, in scenario number one, let's say scenario number one, the load is acting at the center. So this is called axially loaded. Or we have only N value. Second scenario, we have moved in one direction only. We have moved in one direction. You can see that the point load is moving in one direction only. So we have N and there is one moment, whether it's X or Y. After you define your X and where is your Y. Okay. Now, third scenario, you will see that you have moved in X and you have moved in Y. So now you have N, MX, and Y. Now, to keep it a bit simple, if we are seeing it in a plan, and this is my center, if the loading is acting here, did I move from my center? If the loading is acting as a red circle, did you move from your center? No. So it means that if you didn't move, then it means that there is no moment. If you didn't move, it means that there is no moment. So it's only N. If you are saying the other scenario, if your loading is acting here now, did you move from your center? Did you move from your center? In how many directions you have moved? One or two directions? One direction. So this is going to be N and M, one M, whether it's X or Y. If we're having another scenario, if we're a scenario where it's like this, okay, where it's like this. Now, how many directions we have moved? How many directions? One as well. Okay, one as well. So it's going to be N and M. Now the third scenario, what if we are having the loading here? In how many directions you have moved? Now two directions. So we have N, we have MX, and we have MY. Okay, so one load, two moments. One moment is going to be due to the to the movement here you have done, due to the movement you have done here, and one moment due to the movement you have done in the other direction. Okay, so two moments. Okay, this one, this case, we call it as axially loaded and biaxial bending. Okay, so we call it as axially loaded and biaxial bending. Uni is 1, bi is 2. Okay, so once again, uni is 1, bi is 2. So axially loaded, there is a load. Biaxial bending, bending refers to moments, so you have two moments. Okay. Now, if you see here, okay, if you see here, let me try to erase if this is possible. Now you can see if, okay, if you have your load here, if you have your load here, okay, if you have your load here, then this is going to be n and mx and then 0. My original x direction is here. My original x direction is here. You have moved my x to here. So there is a moment in terms of x direction. Okay, my x reference has moved. So there is a moment about x direction or x axis. If my loading came here, my y-axis should have been here. My y-axis should have been here, but now it has been shifted to this. It has. Okay, it has been shifted to this place. Okay, so now what will happen? You will be having n, my, and then 0. Are we clear? Are we clear? Okay. So now we explained the meaning of mx, my, n actually loaded, uni actually loaded, and it goes on. Okay. Let me try to demonstrate for you before going into design. Okay, let me just try to illustrate for you. Just 1 second. Okay. Now you just see here. Yesterday, if you remember, I have tried to explain for you that how the values will be different in terms of Lx and Ly. If you remember when we have talked about L0 x and not y, if you remember. Okay. Now if you see here, if you see in this example, we have beam only in one direction. Okay? We have beam in one direction. It means if I rise my mouse from here, this is going to be the height of the column from here to here, and it will stop because of the beam. If I go and take it from the other side, if I go and take it here, then it's going to go from the top till the end, that there is no beam. Can you see that it differs from one direction to another direction? Can you see in this direction that the column is nothing stopping it till the end? While in the other direction, we have beam stopping it. Can you see? Can you see this? Okay, so now if we see, if you go and see, if you go and see, you will see in one direction the column has been taken to be 3.1. In one direction, the column has been taken to be 3.1. So if we take that direction, we need to reduce the column size or the column height actually 3.5. So 3.5 minus the depth of the beam 0.4, so we have it as 3.1 in one direction. In the other direction, we have it as 3.5 because the column is going to go from the beginning till the end. Okay? There is no beam stopping it. Now in this scenario, the column has not been stopped by anything. In this scenario, the column has not been stopped by anything. So the column should have the full height in both directions. So if we go and see now, you can see in the first direction it's 3.5. In the second direction it's 3.5 as well. There is nothing stopping my column from any direction. Now if we go here, check this particular column, you can see there is a beam in one side, there is a beam on the other side as well. So in both sides we have the column having a restraint. So if we click now and check, you can see in the first direction we have it to be 3.1. In the other direction we have it at 3.1 as well. Are we clear how the length is changing from one direction to another direction? Is it clear? The matter of Lx and Ly? Okay. So once again, it depends. It depends on the side of the beam. If the beam is available in both sides, you need to reduce the size of the beam. If the beam is only available in one side, then you need to reduce only in that side. If the beam is not available in any of the sides, then you don't need to reduce anything. So we have seen a column where it's only having a beam in one side. We have seen a column which is having no beams. We have seen a beam or a column which is having beams on both sides. So that will give you that will give you the case of the value of L0 for X and L0 for Y. Okay, because they will differ. Let us try to understand. The uniaxial, axial, and biaxial when it comes to real situation and let's say in terms of software, because software can show you in 3D. So that's going to be a little bit easier. So let us say that I have 3 models. Let us start first with the first model. So 0, 3.5, and 7. And then this is 0. And then this is 0. No. Each case is different from the other one. Okay. And I try to draw one column. I try to use an RC column. Don't worry about the steps. I'm just trying to draw for you the beams and the columns. Okay, let me have columns as well on the other side. Okay, so I have drawn columns. Okay, I have drawn columns. Okay, I have drawn columns for me here. Okay. So we have drawn columns. the span for the beams, if you see, dimension. Okay, the first beam is 3.5 and the second beam is 3.5. Okay, so we have the first beam. We have the first beam to be 3.5. Okay, so we have two beams. And this two direction, it will differ if you're having beams, if you're having no beams. If you mean that you're having the beams in the same direction, okay, in only one direction, then at that time one length will be affected, either x or y. If you are having the beams in both direction, x and y, then your height of the column will be changing for both x and y. Okay, so we have done a column. We modeled the column. We modeled beams with the same height, with the same lengths, and we are trying to apply some load. Okay, we are trying to apply some load. So let me just say that I have a load of -5, for example. I'm going to apply -5 here and -5. So -5 and -5, or 5, W is 5, L is the same, L is the same. We should be getting the same bending moment, right? We should be getting the same bending moment. Do you agree that we should be getting the same bending moment? Okay, so now if we go and calculate, okay, if we go and calculate, let's just put the grades of concrete, the grades of steel. Okay. So now I want to check the bending moment. If we go for the results and then the diagram, we can see M1. Now, can you see which column has shifted? Did the column which is at the center shift from its position? Did the column shift from its position? No. Why didn't shift? Because the moment of the first span and the moment of the second span are equal to each other. Let me try to make it a little bit more clearer. So you can see 4.63 here, 4.63, and then we have 8.61 for the moment in this side, 8.61 for the other side, and the moment of the column is equal to 0. Okay, the moment of the column is equal to 0. So in this case, this column is only taking an axial load. Okay, the column is taking an axial load because the moments are contradicting each other. Okay, the moments are contradicting each other, and then your load will not move from the center. Now, what about this particular element? Do you have the moment in one direction? Do you have the moment in one direction? Do you have the moment in one direction? This column. We have the moment in one direction. We have in one direction. So this column will be designed as axially loaded and uniaxial bending. Okay, this will be designed for axially loaded and uniaxial bending. Now, if we want to modify a little bit, okay, if we want to modify, and let us say I want to have the other side to be 4 meters. Okay. So I want another frame. So I'll just take these. Okay. So I just copied these beams, and then I'm going to draw extra beams as well. So I have drawn. Let me just remove the results now. Okay. So if you can see here, we have a 3D. Okay, we have a 3D structure now. Previously we were having 2D. So in 2D, it's not possible for you to have biaxial. In 2D, it's not possible to have to have biaxial moment, because moment is happening in one direction, the other direction is not available here. Okay. So now in this scenario, when it's a 3D, we can see two moments happening. Okay, so let us try to have a loading. Let us have a loading. You can see that these have already been loaded. So -5 here, here, and then here. Okay, and then we'll calculate once again. Change everything to C30. Okay. So now we have modeled these beams and columns. Okay, we have modeled these beams and columns, and we want to see now what is happening. So we'll go for results, diagrams. I'll switch on MY. Let me just try to remove the beams. Now you can see that we have moments. If we take, for example, this particular column, let us isolate this particular column. Now, in how many directions you can see the moment? You can see that the moment is happening only in one direction. Can you see that the moment is happening in one direction, which has been given for you here as MY only? That is only in one direction. There is nothing in the other direction. Now, if we allow going for MZ, you will see now how many moments will be there. How many moments are there? How many moments are there? Okay. There are two moments. Why two moments are there? If you go and take this beam, okay, okay, you will see that this particular beam is going to push your column in that side. So that's why you are saying that the column is pushed outside. In this side, this beam is going to be pushing my column in the other side. So that's why you see the red color or the pink color. Can you see what's happening? Can you see that the beam is pushing the column in the opposite side? Is it clear that now we have two moments? Are we okay? Are we fine? Now going here, we'll take these beams, we'll isolate them, going for MZ. Now you can see here, what do we have the moment? Okay, in how many direction we have the moment? Okay. In how many direction? Okay. See for this column, in how many direction you have the moments? For this column, how many direction? For the column, not for the beam. For the column, how many direction of moments are there? Only one direction. Okay. The column is moving only in one direction. The other direction is counteract, what you call, it's counteracted by the other moments. You see, the column is moving now in one position only. You can see because of this beam, the column is pushed here, but we don't have any value on the other side. Once again, here, 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 then here. Okay, so I try to isolate certain elements. Now you can see for this particular column, how many moments are there? For the column on the edge, how many moments are there? Can you see that there are two moments? One is mx and one is my. What about this column now? Do we have one moment or two moments? This column, one moment or two moments? This column, only one. So we have two here, we have one here. Okay, one here, and then we have two. Let us see the scenario when there is no moment at all. Okay, let us see a scenario where there is no moment at all. Okay, so I'll just try to model something. So I'll just have. Okay, so I'm just trying to give you the different types, I mean different cases, and we'll see how it will behave. Okay. Now let us see the different scenarios. Okay, let us see the different scenarios. First, let us see the loading. How much is time? Okay, so the loading is the same. Okay, the loading is the same. We want to check now we want to check the bending moments. So we go for mx, oh sorry, my and mz. Okay, now you can see here, if we go and take if we go and take different cases, here we have two moments. Okay, here we have two moments. Here we have only one moment. Here we have only one moment. Here we have only one moment. Here we have two moments. Here, if you see, due to the fact that this beam is giving you a little bit more moments, you can see that the beam is leaning in one side. Okay. So once again, it depends. It depends on what are the beams, whether you will see an axially loaded, whether you will see uniaxial, or you will see biaxial. Now, have you understood? Have you understood in reality or in software how these are found? Because the values of n, mx, and my, these values are calculated from the software. N, mx, and my, normally they are calculated from the software, so you should know how to get them. You should know how to get them. And if you notice, we have, let us take this one. If you notice, we have values at the top. So we have mx for the top, my for the top, and we have mx for the bottom and my for the bottom. Okay, so two values at the top, two values at the bottom, and you need to design for that. Some software packages, they are asking you only for one moment. Okay, one moment only to design for the highest moment. Some of the software will ask you for more accurate values which are bottom on top, which will give you more accurate reinforcement. So you need to be careful. You need to know how to calculate or how to get these values, which are n, mx, and my, if any. Okay. Returning back to our PowerPoint. Now for case number 1, we have learned that we are going to use the equation. For case number 2, we are going to use the chart. For case number 3, we are going to use the chart as well. Okay, we are going to use the chart as well, but if you have seen the charts, it is only one moment here. Okay, it's only one moment here, where B has been given at the width as the width of the section, H has been given as the height or depth of the section. So we have one moment, and we have one N. Okay. Now, in case of a biaxial, we have two M values. We have MX and we have MY. And the code has given you two equations. One is MX dash and one is MY dash. Now, which one to choose is going to be depending on a certain condition given by the code. So if we go to the code, it says for you, for biaxial bending, if your MX over H dash is larger than MY over B dash, then the dominant moment is going to be X. So we are going to calculate MX dash. If your MX over H dash is lesser than MY divided by B dash, then the dominant is going to be MY, and we need to calculate MY dash. So now, after doing that, you are going to calculate only one moment, whether it's MX dash or MY dash. And that value is going to be used in the chart. Once again, in case of a uniaxial, you have only one moment, and directly you will be using the chart. In case of a biaxial, you need to get either MX dash or MY dash, which is going to be representing, you notice, if I'm calculating MX dash, it represents MX plus a certain percentage of MY. If it's MY dash, it's MY plus a certain percentage of MX. Okay, so we are trying to combine these moments together in one moment. It's like getting the resultant of both moments. Okay, and we'll learn how to solve. We'll learn how to solve for biaxial bending. Hopefully today I'm going to cover axially loaded column. Next week most probably another lecturer will be coming for your class. Okay, next week and maybe a week after. If I was not able to come, then the other lecturer is going to take the remaining part of the columns. Okay. Anyhow, today we are going to solve one problem in terms of axially loaded. Okay, we are going to solve one problem or two problems of axially loaded, and then include column in the test. Do you want the column to be included in the test? Do you want column to be included in the test? So column is not included. Okay. Although columns is easier for you. Anyhow, okay. So column is not included. So it's going to be only the foundation part. Okay. So it's the foundation part now. Foundation for test 2, it's going to be foundation. Whatever you have studied in the foundation. Okay. So isolated, combined, isolated with this centricity, everything, shear, everything is in foundation. Okay. Only foundation, yes, only foundation. Only a small topic. If we have got the permission to have test number 3, we are fighting for test number 3. If we got the permission, then test number 3 is going to be for your card. Okay. So problem number 1, it says for you a short-based column. Short-based column has FCU. It has an FCU of 30, an FY of 460. is required to support an ultimate axial load of 2000 kilonewton. Determine a suitable section for the column if the area of the longitudinal section ASC is of the order of 3% of the gross sectional area of the column. So let us take this particular question, and then we'll solve it in the whiteboard. So we'll have a little bit extra piece. We're having this problem. So a short braced column that has FCU of 30, FY of 460 is required to support an ultimate axial load of 2000 kilonewton. Determine a suitable section for the column if the area of the longitudinal seam ASC is of the order of 3% of the gross sectional area of the column. Now, what we need to understand, we need to go and get the inputs. So for the inputs, they have given me that we are going to use C30. They have given me that we are going to use C40 or C in FY460. FY460 is required to support an ultimate axial load. So we have the value of N to equal to 2000 kilonewton. Determine a suitable cross section. So they want us to calculate cross section. When we refer to the cross section, we are referring to, in case of a square, we are referring to V. In case of a rectangle, we are referring to V into H. In case of a circle, we are referring to a diameter. Okay. They said for you, if your ASC, so if your steel is 3% of the area of the column. If they said for you that your ASC is 3% of the area of the column, you need to calculate the cross section. Now, one thing that we need to do, one thing that we need to conclude and know. Do you agree with me that saying area of column is equal to area of concrete plus area of steel? Do you agree that in the column we have only concrete and steel? Do you agree? Okay. Now, if I said for you, area of column is equal to area of concrete plus area of steel, you are telling me that area of steel is 3% of area of column. Can we compute for area of concrete now? If you are telling me that steel is 3%, then your concrete is how much? My concrete is 97% of area of column. So now I can conclude saying area of steel is equal to 0.03 area of column. And I can say that area of concrete is 0.97 area of column. Do you agree? Do you agree about this one? Now we said here, this is going to be case number one. Case number one, where it's only N value. There is no moment on the other side. Okay, there is no moment in X, there is no moment in Y. They didn't mention any moment for it, so it's actually loaded. Okay, so what we need to do, we are going to calculate. So N, we said, if it's actually loaded, we are going to use an equation. So the equation says for you, 0.4 FCU area of concrete plus 0.8 FY ASC. Now N has been given for me. N has been given for me that it's 2000. Now in terms of kilonewtons, so I'll just multiply it by 10 to the power of 3. So 2000 into 10 to the power of 3, 0.4 into FCU. FCU has been given in the question to be 30. Area of concrete we have calculated it as 0.97. So 0.97 area of column plus 0.8 Fy is your 460. So 460 multiplied by area of steel, which is 0.03 area of column. Now you can see we have only one variable, that is area of column. So 2000 into 10 to the power of 3 is equals to, it's equal to 0.4 into 30.97. This is going to give you 11.64 area of column plus, sure, it's direct, 3% is steel, then concrete is going to be how much? It's going to be 97% of course, because there is nothing except steel and concrete in the section. 11.01 area of column. So my area of column is equal to 2000 into 10 to the power of 3 divided by 11.64 plus 11.00. Okay. So now we have 2000 multiplied by 1000 divided by 22.68. This is going to give you 88,180, let's say 84 square meters square. Okay, I don't know how did you calculate it to be 16,000. How did you calculate it to be 16,000? Okay, which is correct. 88,000. 88,000. Okay. So now I can assume, because the question didn't ask me to have any type of section, so I can assume the easiest section, which is a square. So now my B is going to equal to under root of 88184. That is going to be equal to 296.6.95. So I can say now adopt a cross section of 300 into 300, and the question has finished. Okay. Okay, so we have got the cross section, and this question has finished. Any question about the question itself? Is there any question? Any question about this one? No question. Okay. We are going to go for problem number 2. Problem number 2. So for problem number 2, we go here. Okay. Once again, this is the question. So it says for you, design the longitudinal steel and links for the 300 mm square short braced column connected to simply supported beams from top and bottom. The column is 3.6 meter and needs to be supported or needs to support the following axial loads. We have GK. GK is representing dead load. QK is representing light load, as we have studied. C30 and 460. So once again, since the question said simply supported beams, so it means that there is no moment because it's a simply supported beam. At the end of the beams, there are no moments. So this one, once again, returns to be case number 1, where it's n 0 and 0. And we are going to use the equation where n is equal to 0.4 FCU, area of concrete, plus 0.8 FY, area of steel. Now, n previously we had the ultimate load. Ultimate means already multiplied by a factor of safety. Now, what do we have? We have dead load separate and we have live load separate. So now to calculate my n is equal to 1.4 into live load, which is 1000, plus 1.6 multiplied by 1000, which is your live load. So if you multiply these two, you will get 1400 plus 1600, and we have got it to be 3000. Okay, so 3000 kilonewton. 3000 kilonewton. Okay. So now I can say n is equal to 3000 multiplied by 10 to the power of 3 equals to 0.4. FCU is how much? FCU is 30. Area of concrete is how much? Now we don't have a percentage, but we agreed saying that area of column is equal to area of concrete plus area of steel. So now I can say that area of concrete is equal to area of column minus area of steel. Can I say like that? Can I say that area of concrete is equal to area of column minus area of steel? Okay, so multiplied by, what is the area of the column? Area of the column has been given to be 350 square. So 350 square, 350 square, 350 square. Okay. 350 mm square, it's not 350 mm square. Okay, so each side is 350 mm. Okay, so 350 into 350, so 350 square, okay, minus area of steel, okay, minus area of steel, okay, plus 0.8 F1 ASC, let's say ASC, in compression since it's in compression. FY, we just start substituting directly, so 0.2, FY is 460, and then ASC is the one that we require. Now you can see that you have only one there was a disconnection. Are you able to hear me? Are you hear me now? Now, are you able now? Are you able to hear me now? Okay. So we said n is equal to 0.4 absolute area of concrete. Still, you are not seeing the screen. Others are not seeing the screen. No screen. I have already shared the gist with you. Now, can you see the screen? Yes, no, no, yes, yes, no, no, yes. Now you cannot see the screen still? Okay, wait. Now yes. Okay, 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 okay. So we have n is equal to 0.4 FC area of concrete plus 0.8 Fy area of steel. We have used the basic fundamental of area of column is equal to area of concrete plus area of steel. And we have substituted the values. Now you can see that we have only one unknown, which is area of steel. So we can go on compute. So 3000 into 10 to the power of 3 is going to be equal to, can you multiply this? 0.4 into 30 into 350 into 350 to the power of 6. Can you confirm? Can you confirm that this is going to give you 1,470,000? Okay. Okay. So 1.47 to the power of 10 multiplied by 10 to the power of 5 to 6. And then we have minus 0.4 into 30. So 0.4 into 30. This is going to give you 12 plus 0.860. It's going to give you 368. Yes. So now what we can do, okay, we can put the AS together. Okay, we can put the AS together. So we are going to have it as 356. 368 minus 12 equals to 3 to the power to 10 to the power of 6 minus 1.47 to the power of 10 to the power of 6. So now we have 356 AS is going to equal to 1.53 multiplied by 10 to the power of 6. So AS is equal to 1.53 into 10 to the power of 6 divided by 356. This is going to give you, I believe, as whatever Amira said, divided by 356, which is around 4,298 meters square. Okay, so now we have got the area required. We have got AS required to be 400 or 4,292. Now the next step is to find AS provided. So when it comes to steel in column, we require two things. We require the diameter. Okay, we require the diameter, and later on we require the diameter and we require the spacing. We require the diameter and we require the spacing of the steel. So now if we go to the BS code, we have got 4,292 98 approximately. So we are going to use beam and columns. Let us choose, for example, 25. So we'll search for something 25 diameter and then something near to 4,298. So the nearest one is 9. Now 9 is a huge number to be kept in. 9 is a huge number to be kept in 300 into 350. So I would rather go for 32. Let's say 32 and 6 bars. We can go for 32 and 6 bars. Once again, 32 and 6 bars. So 32 and 6 bars is going to give you an answer of 4,830. Okay, so we are going to adopt. We are going to adopt. We are going to adopt 4,830. 4,830, which is representing 6 bars of 32 diameter. Okay, 6 bars of 32 diameter. So my diameter is, I have 6 bars of 32 diameter. Okay, the spacing according to the code, we return back to the code. By the way, the minimum, we said the minimum diameter for a column is 12. I believe I have told you last class. So column, we close this one. And we go and search for spacing or links. Okay, so here it says for you, when part or all of the main reinforcement is required to resist compression, which is the case of a column, links or ties at least 1/4 the size of the largest compression bar, or 8 mm, whichever is greater. Now, of course, in the code it says 6 mm. In the code it says 6 mm, but we don't have 6 mm in the market. So it is 1/4 of the size of the member. Okay, one quarter of the size of the largest compression bar, and or 8 mm, whichever is greater, and then should be provided at a maximum spacing of 12 times the smallest compression bar. Okay, so we'll return here. We said the diameter of main steel is the diameter of the main steel is 6 bars of 32. Okay. Let us go for the links now. Links. Now, in case of a diameter, they told us you have two conditions. Condition number one, 1/4, if you remember, it says for you 1/4. Okay, 1/4 of the size of the largest compression bar, or 8 mm, whichever is the greater. Now my bar, whatever we have chosen, is 32. So 1/4 multiplied by 32 is 8 mm. Second option says for you 8 mm. So once again, 1/4 of the largest compression bar. We didn't use largest and smallest. Largest and smallest will be happening if you have two bar sizes. Now we use only for the main bar, we use only one bar size, which is 32. So there is no smallest and largest. So 1/4 of 32 is 8 mm, or 8 mm. It says for you whichever is the greater. So picking any one is fine. Okay. Now the second thing is going to be the spacing. And the code says for you. Okay, and the code says for you, in case of a spacing, it should be provided at a maximum spacing of 12 times the smallest compression bar. Once again, we don't have smallest and largest. Okay, so we go spacing equals to 12 times of 32. Okay, that is going to give you around 368. Around, right? Or 86, 360. 32, 384, 380. Okay, 380. So now the last thing is for me to draw the cross section. So my cross section is 350 to 350. We have a length. We have a length. Now this length is provided as T8. The grade is T. 8 mm is the diameter provided at a spacing of 384 millimeter centimeter to centimeter. Okay. So the diameter of the link is 8 mm as we calculated. Spacing is 384. How many bars are there? We have 6 bars. So bar number 1, bar number 2, bar number 3, bar number 4, and then you can have here bar number 6. Typical cover is shown. Typical cover is calculated as long as they didn't give you the conditions of water and fire. Okay, so we have 6 bars. We have 6 bars of 32 diameter. And if we see as a longitudinal section, we see a longitudinal section. If we see a longitudinal section, so now you can check for the cover if you are designing for a certain condition, which is mild or moderate or fire or whatever. Otherwise, you can provide the minimum cover. Okay. So now, if you can see, we have the first bar, we have the second bar, we have the third bar, and then there is a link between them. And this is just a section. The spacing between one link to another link is 384 mm. And this is the end. Whatever we have solved now. This is the end of 10 marks question, which is having the same value of designing a foundation for 10 marks. Okay. So in your final examination, hopefully you will be having column problem for 10 marks, foundation problem for 10 marks, slab problem for 10 marks. Okay. So normally, if you compare, column chapter is the easiest chapter where you can score a lot of marks. Anyhow, we'll keep chapter number or column chapter to be for test number 3 if there is any test number 3. Inshallah. Any question that you have before we finish up the class? Before we finish the class, do you have any question?
Sir, I have a question.
Yes.
Sir, the length, the diameter which you calculated 1/4 into the 32. 1/4 is the rule?
Yeah, it says for you. I have showed you the code. The code says for you 1/4 the size of the largest compression bar. 1/4.
Yeah, I got it.
Any other question? Because the code says for you maximum spacing of 12 times the smallest bar size. 12 multiplied by 32. Compression bar. It didn't say for you links bar. Links is not going to protect you in compression. Links is going to protect you only in terms of shear and linking. It's not a compression bar. Which I have already said. It's foundation only. Okay, you think you start thinking, okay, you start thinking, why in the diameter we are using the largest, and why in the and why in the spacing we are using the smallest? Why not both of them largest, or both of them are the smallest? And why they have mentioned smallest and largest from the beginning? Now, in our problem, we don't have smallest and largest because it's only one size that we have used. But why the code has said largest for the diameter, smallest for the spacing? Okay. You just think of it.